Jai Hind everyone. I am VIKAS RATHI working in Ajay Kumar Garg Engineering College as an assistant professor. Today the subject which I am going to discuss is engineering physics. The subject code is BAS 101 and the topic which I am going to discuss is diffraction due to single slit. References are for this textbook of optics by Ajay Ghatak, optics by Brijlal and Subramaniam, a textbook of engineering physics by Navneet, and the engineering physics by S.K. Mehta, engineering physics by S.L. Gupta. So these are the references for this topic. In diffraction, there are many topics like introduction, diffraction, types of diffraction, diffraction due to single slit, diffraction due to double slits, diffraction due to plane transmission grating or end slits, resolving power and Rayleigh's criteria of resolution, resolving power of plane transmission grating. So these are the topics in diffraction. Today I will give a brief introduction of diffractions, what is diffraction, types of diffraction, then I will give about the idea about the resultant of n simple harmonic motion, and then I will discuss the diffraction due to single slits. So mainly I will focus on this topic, diffraction due to single slit, but in brief I will discuss these topics also, introduction also. So first I will discuss what is diffraction. What is diffraction? Basically, when light falls on obstacles or small apertures whose size is comparable with the wavelength of light, the light bends around the corners of the obstacle and enters in the geometrical shadow region. So this bending of light is basically called the diffraction. And the requirement is the basic requirement for good diffraction effect is that the size of the aperture that should be comparable to the wavelength of the light source. Here you can see there are two types of aperture. In first case there is a wide gap, so diffraction effects will be small in this first case. But if the gap is narrow, if it is of the order of the wavelength of light source, then you can see then the diffraction effects will be maximum. That means the spreading of the wavefront that will be maximum. That means here in second case, in case of narrow gap, in case of narrow gap, you will see the more diffraction effects here, right? So that means for diffraction, what should be the condition? Wavelength of the light source that should be of the order of size of the aperture. Then you will see the maximum diffraction effects. There are two types of diffractions. We can categorize diffraction in two category, Fresnel's and Fraunhofer. The basic difference between Fresnel and Fraunhofer type of diffraction is that in case of Fresnel diffraction, the source and the screen, they are placed at finite distance from the aperture. But in case of Fraunhofer type of class of diffraction, source and screen, they are placed at infinite or long distances from the aperture. Here you can see in first case, this picture shows the Fresnel type of diffraction, and you can see here that the distance from source to the slit and slit to the screen, that is finite here. So there is no requirement of lenses in this first case in case of Fresnel type of diffraction. But second, this is a Fraunhofer type of diffraction. You can see that a light source that is at infinite distance from the slit, and similarly the screen that also at the infinite distance from the screen. That's why in case of Fraunhofer type of diffraction, we use the lenses here, because light source will be at infinite distance or at long distances here. So this is the basic difference between the Fresnel and Fraunhofer type of diffraction. Here again I repeat, in case of Fresnel diffraction, light source and the screen, they will be at finite distances, and in case of Fraunhofer type of diffraction, screen and light source, they will be at long distances, at infinite distances, you can say roughly. So to find out to discuss the theory of the single slit, first I will give a brief introduction, resultant of n simple harmonic motions, because we will use that formula in case of single slit, diffraction due to single slit. So first I will give a brief introduction about how we calculate the resultant of n simple harmonic motions. So to find out the resultant of n simple harmonic motions, we can consider here if amplitude, simple harmonic motion, they have equal amplitude A. If this A represents the amplitude, okay, and the period of phases, they are increasing arithmetical progression by amount delta. That means the phase difference between the two successive vibrations, that is delta here. Then to find out the resultant, okay, due to n simple harmonic motions, okay, in this we can use the vector addition method or vector polygon method here. So according to that method, this amplitude A will represent the length of the vector, and the phase between the two successive vectors represents the angle between them. So in this way, by using this polygon method or vector addition method, we can find out the resultant of n simple harmonic motions or n number of light sources. So this diagram shows here that if we have n number of simple harmonic motions, so this will represent here, this will represent these vectors here, length of the vector A here, okay, then next vector, okay, if this angle is delta, so angle between them will represent delta here, then again the length will be same, okay, this will be equal to the amplitude of the vector and so on, and this R, this will represent here resultant vector. So to find out the resultant vector, here we will take the component of R, okay, in horizontal direction and in vertical direction. So in horizontal direction, the component of R, that will be here R cos phi, and this will be sum of all these components. That means here the horizontal components, they will be A, okay, and next component will be A cos delta and so on. So then final last component will be A cos n minus 1 into delta. So here first we will write the horizontal component of the resultant vector, that means along x directions. Then we will write here the vertical components of the horizontal this resultant vector R. So that will be R sin phi. So in this way, from equation 2 and 1 and 2, by solving them, we can find out the resultant vector value of the R. So for that purpose, what we will do, we will multiply equation 1 by factor 2 sin delta by 2, this factor, and similarly here, okay, we will apply this also here sin delta by 2. So again equation 2, that also multiplied by 2 sin delta by 2 factor, and by solving them we can calculate the value of R. Like if we multiply this equation 1 with 2 sin delta by 2 factor, so then this left hand side becomes 2 R cos phi sin delta by 2, and if we take this A common, then we will have this first term 2 sin delta by 2, 2 sin delta by 2 into cos delta and so on. Then by using this formula 2 cos A sin B formula, the value of this is sin A plus B minus sin A minus B, okay. So by using this formula we can simplify this expression, okay. So this will becomes here A 2 sin A delta by 2, that will, this first term remain same, and here if we apply this formula, then this term becomes sin 3 delta by 2 minus sin delta by 2 and so on, and last term that will becomes, this is half here and minus half into delta and minus sin and minus 3 by 2 into delta and so on. And if we simplify this, here you can see that these terms, they will cancel out, this also cancel out, okay, and finally we will have these terms, remaining terms here, this term and this term, this also cancel out here. So finally after simplifying, we have the value of 2 R cos phi sin delta by 2 will be A sin delta by 2 plus sin n minus half into delta, and then again we will use here sin A plus sin B formula. For by using that formula, here the value of 2 R cos phi into sin delta by 2 becomes here 2A sin n delta by 2 and into cos n minus 1 into delta by 2. Okay, from this last equation we can write the value of R cos phi here. So R cos phi becomes in this form A sin n delta by 2 upon sin delta by 2 into cos n minus 1 into delta by 2. So suppose this is equation 3 here. So simply we can calculate the value of this, okay, here R sin phi, okay, value, to find out the value of R sin phi, then again we will multiply equation 2 by this factor 2 sin delta by 2, again simplifying with the same manner, and by simplifying them we can find out the value of R sin phi, and it will be in the same form here, just there will be a change here, it is cos term and here it will be sin term. So by dividing equation 3 and 4 here or if we want to find out the resultant amplitude, that means value of r here. So what we will do, we will square and add equation 3 and 4. So by squaring and adding equation 3 and 4, we will have the value of r square, and r square will be in this form here. So r square will be equal to a square sine square and delta by 2 upon sine square delta by 2, right? So that means value of r will be here. If you take the square root of this value, then it will be a sine and delta by 2 upon sine delta by 2. So this will be the resultant amplitude here. So to find out the resultant amplitude in case of single slit, we will use this formula there. Okay. If you want to find out the resultant direction of the resultant this component or this resultant vector r here, so this will be by dividing equation 3 and 4 here, we can find out the direction of this resultant vector r here. So generally we will use this formula here to find out the resultant amplitude here. So r represent resultant amplitude, a represent due to the amplitude due to one slit, okay, one vibration, and this n number of vibrations, and delta represents their phase difference. Okay. So we will use this formula here. So now I will discuss our main topic, which is Fraunhofer diffraction due to single slit. Okay. So to discuss the theory of the single slit, first of all we will discuss what will happen in case of single slit, what is single slit, how diffraction occurs due to the single slit here. What will happen when a light beam is incident normally from a light source S on a narrow slit AB of width E. Here you can see this is slit AB, okay, and suppose the width of slit AB is E here, small e here, okay. What will happen is, because this is Fraunhofer type of diffraction, that means light is coming from a long distance. So that means the wave front which will incident on slit AB, that will be in the form of plane wave front, okay. So what will happen when this plane wave front will incident on slit AB, okay, then according to Huygens wave theory, what will happen, each point on this wave front will act like a second source of light, okay. So that means here on slit AB, when this plane wave front will reach on slit AB, then each point on this wave front will act like a secondary source of light, and when they will pass out from this slit, they will get interfere. So due to their superposition or due to their interference, we will have resultant intensity on screen, and the value of intensity that will depends upon the phase difference and path difference between the interfering wavelets or small wavelets or secondary wavelets, right. So first of all we will find out the resultant intensity on screen at point P. In general, if we consider this point P, then first of all our problem is to find out the resultant amplitude or corresponding intensity at point P due to superposition of n number of slits. So here this AB, this is a single slit. Here we have considered the slit size E here, okay. Now if you want to find out the path difference, okay, for this point P, okay, what will happen, the path difference will be here this value, this delta here, okay. So to find out the path difference, what we will do, we will do this, use this relation, phase difference equal to 2 pi by lambda into path difference. So we can find out easily the path difference between the wave fronts which is originated from point A and B. So that will be equal to this distance, and this distance can be calculated easily because here we have considered that these wavelets, secondary wavelets, they are diffracted at an angle theta. So this is the angle of diffraction theta here. If this is angle of diffraction theta here, then this angle will be 90 minus theta. So this angle will be equal to theta here. If this is theta, then in triangle AB, if we consider this point C here, so in triangle ABC, the value of path difference, that means value of BC, that will be equal to this E sin theta, AB sin theta, and AB equal to E. So this will be equal to E sin theta. So that means the path difference will be here AB sin theta, okay. So this will be equal to E sin theta. So here this point AB sin theta. So this point here they consider this N here basically normal, okay. So we can put this point here N, then what will happen by using if we want to find out the phase difference, so we know that this relation phase difference equal to 2 by lambda into path difference. So in our case path difference is E sin theta, so this will be 2 pi by lambda into E sin theta. So we have calculated the phase difference here, resultant phase difference, that means phase difference between the wavelets which is coming from point A and B. Now if we divide this slit AB into n equal parts, okay, then if we consider that amplitude coming from each part, from each section of the slit AB, that is small a here, this is small a, okay. So the phase difference between the two successive points, that will be the resultant phase difference, which we have already find out, that is 2 pi by lambda into E sin theta. If we divide this value with n, then we can calculate the phase difference between the two successive point sources. Between the two successive point sources means between the two consecutive points here. So that can be calculated by dividing this resultant phase difference to that value, okay, in which we have divided that slit. If we divided that slit in n number of slits, okay, so then the phase difference will be 2 pi by lambda E sin theta divided by n here. And if this is delta, right, if we assume that value equal to delta, so here delta will represent what? Delta will represent here, delta will be the phase difference between the two successive point sources, okay, and A will represent here amplitude coming from each slit. So then here in case of single slit, we can use the vector addition method or vector polygon method. So according to that method, what A will represent? A will represent length of the vector, and this delta will represent their angle between the two successive vectors. So here we can apply that method, vector addition method, vector polygon method, to find out the resultant amplitude due to superposition of n number of slits, n number of secondary waves, right. So then we have find out this formula, okay. So that R was R equal to A sin n delta by 2 upon sin delta by 2 here. Now in our case, what we have find out? Delta. So in our case, in case of single slit, what is delta here? So delta is 2 pi by lambda E sin theta divided by n. If we put this value of delta in this equation, then we have this sin n pi E sin theta by lambda divided by here again sin pi E sin theta by n lambda here, okay. If we put this value here, pi E sin theta by lambda equal to alpha, if we put this value in simplified form here, okay, so we can take this coefficient of sin, that means value of theta here in terms of alpha. So alpha will represent here pi E sin theta by lambda. So that means this equation becomes what? This equation becomes, the value of R now becomes A sin alpha upon sin alpha by n. This is n here, okay. Now because n is very large, we have divided that slit in large number of n number of parts. So n is very large, and if n tends to large, then value of sin alpha by n tends to alpha by n, because we know that if theta is very small, then sin theta tends to theta here. So that means this value becomes alpha by n here. So that means resultant amplitude, that means resultant intensity at point P becomes now, that will be equal to R, amplitude will be equal to R. So that will be equal to A sin alpha upon alpha by n, and now this alpha multiplied with this A, so it will becomes Na sin alpha by alpha. So this A represents amplitude due to one slit. So if we multiply with n, so it will give the resultant amplitude due to n number of slits. So this means Na will represent maximum amplitude, okay. So this will be, if Na here A, so A will be the maximum amplitude, and it will be the times sin alpha by alpha, right. So this is the amplitude, value of the amplitude at point P. Now if you want to find out the intensity at point P, so what we will do, we know that intensity proportional to amplitude square. So that means intensity will be proportional to A square sin alpha by alpha whole square. Okay. So this is the resultant intensity expression due to the single slit here. Now if we that means you can see here that intensity at on screen, okay, at some points, that will depends upon value of alpha, and value of alpha is related with the this expression, that means value of theta here, that means angle of diffraction. That means the intensity will be the value of intensity will be different at different points. It will depends upon the angle of diffraction, okay, because it depends here value of alpha, so it will depends upon the value of theta, angle of diffraction here. So if you want to find out the condition for the maximas and minimas, the value of intensity, okay, where intensity will be maximum, where intensity will be minimum, so that will depends upon the angle of diffraction here. So in case of single slit, okay, in front of the screen there will be maximum intensity, and that maximum intensity, the value of the maximum intensity, that will be for the central maximum. So that means the condition for the central maximum here, angle of diffraction at center will be 0, so theta will be 0. So if theta will be 0, then according to this condition, because theta is 0, so then alpha will be 0 here. So if alpha is 0, then we can find out the value of this factor with limit alpha tends to 0 sin alpha by alpha, this the value is 1 here, okay, we know that with limit alpha tends to 0 sin alpha upon alpha tends to 1. If this is 1, then intensity at the center maximum will be maximum, and it will be equal to the I naught here, right. So that means at central maximum the value of intensity will be maximum, and which will be proportional to the I naught here. Now between two successive there will be large number of minimas on the screen, okay, where intensity will be minimum. Now to find out the condition for the minimas, okay, to find out the condition for the minimas here, what will we do? That means value of this expressions, what was the expressions for intensity? Intensity equal to, this was a square, or if we put that a square I naught, that was sine square alpha upon alpha square. So that means for minimum intensity, the I must be minimum. Minimum means it may be 0, and it will be 0 if sine alpha equal to 0 and alpha not equal to 0, right. If alpha will be 0, then again it will give condition for the central maximum. So for minima, sine alpha will be 0 and alpha not equal to 0. If sine alpha will be 0, then alpha will be plus minus some integer, if it is m, so it is plus minus m pi, and the value of m will start from 1, not from 0. M cannot be 0. If m will be 0, it will give condition for the again central maximum. So m cannot be 0. So that means the value of alpha here, that they may be plus minus pi, plus minus 2 pi, plus minus 3 pi, okay. So these are the conditions for alpha for the minimas here. Now if you want to find out the condition for the minima, okay, equation for the minimas, so then we know that alpha was alpha equal to pi e sin theta by lambda, okay. So alpha equal to pi e sin theta by lambda, or and this value of alpha here, this is plus minus m pi. So if we equate them, then what will happen? We have this equation e sin theta equal to plus minus m lambda, right. So this condition is known as condition for the minima, right. Now between two minimas there must be maximum intensity, and those points, okay, on screen, okay, they are known as secondary maximas. So to find out the condition for the secondary maximas, what we will do, we will use that condition. If we take here first derivative of that function equal to 0, so that will give condition for the maxima, okay, because we know that to find out the maximum and minimum value of any function, first derivative of that function should be equal to 0. So that means function is over here intensity, so that means derivative of intensity, that means I with respect to alpha, that should be equal to 0. So di by d alpha will be 0, and alpha, what is alpha here? Alpha is I naught sin square alpha upon alpha square. So that means we will differentiate this equation with respect to alpha here. So if we differentiate this equation with respect to alpha, so this will becomes this I naught, this is constant here, and value of this we can use this here. This is the first function, and 1 by alpha square is the second function. Then first function derivative of second, that means 1 by alpha square derivative of alpha, 1 by alpha square with respect to alpha will be minus 2 by alpha cube. Then second function 1 by alpha square and derivative of sine square alpha, it will be 2 sine alpha into cos alpha. Okay, we know this. If we take this common I naught 2 sine alpha by alpha cube, then in bracket we have this value minus sine alpha plus alpha cos alpha, which will be equal to 0. Now according to this condition, according to this equation, either this factor 2 sine alpha upon alpha cube will be 0, or this value which is in bracket will be 0. So this sine alpha cannot be 0. If it will be 0, then it will give condition for the minimas. So that means for secondary maximas, this must be equal to 0. That means this value must be equal to 0. So if it will be 0, then we will have this condition sine alpha equal to alpha cos alpha, or it will give this condition alpha equal to tan alpha here. So this alpha equal to tan alpha, this is the condition for the secondary maximas. Now we can solve this condition by using the graphical method. Let this is equal to y here. So if it is y equal to alpha tan alpha, then we have two equations, two simultaneous equations. That means one is y equal to alpha and another one is y equal to tan alpha. Okay, so we have two equations, two simultaneous equations here. Now this y equal to alpha will represent equation of a straight line, and y equal to tan alpha represents discontinuous curves here. So that means if we can solve these equations by graphical method, here the intersection points of these two graphs, that will give the solution of these equations here. So that means if we draw a graph between y equal to alpha and y equal to tan alpha here, this is y axis, this is x axis here. Okay, so here on x axis we will take the value of alpha. For alpha equal to 0, okay, we have this point here. Then we have this y equal to alpha represents equation of a straight line, and slope is a 45 degree. So this will represent, this equation will represent here y equal to alpha, right? And these are the discontinuous curves. These are the discontinuous curves for the tan alpha here. Okay, so these values here. Now we can see the intersection points will be at approximately at alpha equal to 0. Next point will be here at nearly 3 pi by 2. Next intersection points will be nearby plus minus 5 pi by 2. Then next point will be plus minus 7 pi by 2. So these will be the intersection points of these two curves. Okay, so that means for alpha equal to 0, plus minus 3 pi by 2, plus minus 5 pi by 2, plus minus 7 pi by 2, plus minus 9 pi by 2. Okay, these values gives the condition for the secondary maximas. But for secondary maximas, alpha cannot be 0, because if alpha will be 0, then it will give again condition for the central maximum. So that means for first secondary maximum, alpha will be plus minus 3 pi by 2. For secondary maximum, alpha will be plus minus 5 pi by 2. For third secondary maximum, alpha will be plus minus 7 pi by 2, and so on. So that means here we will have for plus minus 3 pi by 2 for secondary maximum, for plus minus alpha equal to plus minus 5 pi by 2 secondary maximum, and so on. Now to find out the intensity at these secondary maximas, okay, we will put the value of if we want to find out the intensity at first secondary maximum. So for secondary maximum, we know that alpha equal to 3 pi by 2. So if we put in intensity equations alpha equal to 3 pi by 2, then we will have the value of intensity at first secondary maximum, which will be proportional to 4 I naught by 9 pi square. Okay, if we put the value of pi here, then we will have that intensity at the first secondary maximum will be I naught divided by 22. Okay, I naught is the intensity at the central maximum. That means at first secondary maximum, intensity will be 1 by 22 times intensity at the central maximum, right? So if we find out the intensity, percentage of intensity at the central maximum, sorry, at first secondary maximum, then so it will be equal to 4.5% only. Okay. Then similarly, we can calculate intensity at the second secondary maximum. We know that alpha for second secondary maximum is here plus minus 5 by 2, and if we put this value here in intensity equation, then we will have that intensity at the second secondary maximum will be only I naught divided by 62. Okay. If you want to find out this value in percentage, then we will multiply with 100 here. So we can calculate intensity at the secondary maximum. This graph shows the relative intensity due to the intensity pattern due to the single slit. Here we can see at central intensity will be maximum. So the value of intensity at the center will be I naught. So it will represent intensity at the central maximum. Then here for pi it will be the first minimum, and this point will represent here intensity at the first secondary maximum. Then 2 pi will represent intensity at the next minima, and so on, and it will represent intensity at the second secondary maximum. So you can see intensity at the other maximas will drastically changes, it will decreases here. Okay. So this is the intensity pattern due to the single slit here. So we can see here there will be one central maximum, and there will be successive secondary maximas, and between two successive maximas there will be minimas here. So this is the resultant intensity distribution due to the single slit. Thank you very much for listening.